This is Sam College, episode 85, for February 4th, 2022. Ham College is brought to you by ICOM. Now's the time to spice up your ham shack with ICOM's new, now shipping ID52A handheld. The perfect radio for staying in or venturing out and working your favorite bands this winter season. Good evening. Welcome to another episode of Ham College. I'm Professor Thomas.
And I'm Dean Martin.
And we have an exciting episode lined up for you tonight. That's because Arnie was expecting an exciting show tonight.
Yeah, so extra excitement per his request.
Yep. So, before we get into it, first thing we want to mention is there's a chat room if you're watching live at the same time on YouTube. We're using the chat right there. You do have to be a subscriber to the AmateurLogic.TV channel because otherwise we can't really moderate the chat and do the show at the same time. So
it keeps the screen door ads down.
It does. Yep. That and the sunglasses porn as well.
Yeah, they're both big deals.
Yeah. Well, It's the weather fitting for the Ham College sweatshirts this week here.
Yeah, the one week out of the entire year.
Yeah, not the whole week, just the last couple of days. Yeah. But it's kind of chilly down here.
Yeah, I don't think it ever got above freezing today. I believe I saw the high was about 32.
It was somewhere right around there. I had some things I wanted to do outside, but I said no, I will be able to successfully postpone that now with a good excuse.
Yeah. I always thought that cold air came from Canada, but Mike says it comes from Colorado.
I can't argue with that because the coldest I've ever been was in Colorado.
Maybe he's onto something.
Yeah. Well, what did we talk about in the last episode of Ham College? Do you recall?
Let me see. Yeah. Coordinate systems, phasers in electronics, not the Star Trek kind, rectangular coordinates, polar coordinates, and phasers again. We talked about phasers twice.
Yep.
We got proof right here in black and white.
Well, I see. Yeah, it's right there. Well, this month we're going to talk about AC and RF energy and real circuits, the skin effect, electromagnetic fields, reactive power, power factor, electrical length of conductors at UHF and microwave frequencies, and microstrip.
Bring on that beautiful buzzer action.
Yep, and the microstrippers. So, yeah, it's you'll know a lot of this stuff tonight.
I hope so.
Yeah.
Because it hadn't been working out like that the last couple of months.
No, you'll know some of this tonight. Some of it, maybe a little challenge. Most of it, I think, if you're general, you'll be familiar with a lot of this tonight. So shouldn't be too terribly bad. What is a result of skin effect? Is it A, as frequency increases, RF current flows in a thinner layer of the conductor or closer to the surface?
Or B, as frequency decreases, RF current flows in a thinner layer of the conductor closer to the surface?
Or C, thermal effects on the surface of the conductor increase the impedance?
Or D, thermal effects on the surface of the conductor decrease the impedance? This one I actually might have a chance on, so I think I may have chosen well, at least for the first question. The skin effect, that's when the current flows on the surface of the conductor, and I believe that's more as the frequency increases that happens more. So I'm going to go with A. RF current flows in a thinner layer of the conductor closer to the surface. Yeah, I think it's A.
Yeah. Everybody is saying it is A in the chat room except for IK04. He's saying it's AE.
Yeah.
So
He must be down there in Emil's part of the country.
it must be. I'm going to agree with you. I believe it's A as well.
Yeah.
The judges say A.
All right.
So
Now, here.
yeah, there
We
you
haven't
go.
done that in a while. Do I need to get some hand sanitizer?
That's all right. I've got some saline nasal spray over here. Inside joke if you weren't here before the show started. All right. Skin effect. Well, we can explain that. The first little drawing there is a cross-sectional area of a round conductor. At DC current, the DC is using the whole conductor. Every bit of it, it's got current throwing through it. As AC frequencies come into play, you can see the center of the conductor is not really conducting as much there. The current is flowing more toward the outer edges of it. As the frequency increases even higher, the skin effect causes a current to flow around the outer edges of the conductor. Why would you be concerned about this?
Well, I don't know. Why would you be concerned about it? Because, I know the skin effect has an effect on antenna building. If you use a larger piece of copper, you're going to have a broader, more bandwidth, basically.
Yeah.
What's the downside of it?
Well, also, particularly it's important on your transmission line because as you increase in frequency, then only the outer part of the conductors are going to be conducting current. Mm-hmm. So on a smaller transmission line, you're trying to shove your current down a much smaller area as the frequency increases. So you have to go to a larger line or a line with less loss. You can run a lot of power on, say, RG8X, and it'll work just fine, 100, 200 feet long on HF. You run a kilowatt on there, and, it might be pushing it a little, but you really wouldn't have that much loss in the line. Mm-hmm. You get up to UHF, and you wouldn't have a whole lot coming out the other end of it. You'd lose a lot in there, so you'd need to take that into consideration, and that's where the skin effect in the conductors plays a part there. Plus, on anything electronics, on printed circuit boards, it'll have an effect on that as well.
Why is it important to keep lead lengths short for components used in circuits for VHF and above? A, to increase the thermal time constant.
B, to avoid unwanted inductive reactions.
C, to maintain component lifetime.
Or D, all these choices are correct. Why is it important to keep lead lengths short for components used in circuits
that
for
looks
VHF
like there's only one really
and above? A, to increase the thermal time constant. Nah, I'm not even really sure what thermal time constant is. There may be such a thing, but I don't think it's going to avoid my thinking here. So I know it's not D. All of these choices are correct. C, to maintain component lifetime. B, to avoid unwanted inductive reactance. Yeah, that makes sense to me because all the other answers are wrong. Uh-huh. And, as you go up in frequency, the lengths of even traces on a PC board have an effect. So the lengths on your components will have an effect as well. Add some inductive reactance in there. That would be negligible down on lower frequencies. But as the frequency increases, every little piece of metal in there could have an effect. So, I'm going to say it's B. Everybody, it looks like in the chat room, says that it was B. So, good for them. I think we're all right. And we are.
Cool. Yeah, I gave you that.
Okay. By the way, Tommy's coughing.
I'm past the COVID stuff, but I can't quite shake this cough.
Yeah.
But I'm not contagious anymore. It's been right at 2 weeks and stuff, so I'm good.
And I had it a little over a month ago, so I'm not super concerned about him sitting over there. And we both were shot 3 times. So.
Live to tell it.
Live to tell it. And I've got my taste back now.
Oh, yeah?
Can't you tell?
So because of who you're hanging around with.
No, it just came back a few days ago. I couldn't taste anything for several weeks.
Yes, I didn't have that problem at all.
Yeah. And I didn't have any coughing.
Yeah, it's really weird how it affects everybody differently.
It is.
And nobody in my family has a coughing problem, but I can't quite shake it.
Yeah, it's strange. It affects everyone different. So I think we probably got off pretty easy compared to some folks.
I'm sure the 3 shots helped.
Oh, yeah, I think probably so. Well, let me ask you this, because I know this is a subject that's near and dear to your heart.
Microstrippers?
Yeah. What is microstrip? Is it A, lightweight transmission line made of common zip cord?
Or B, miniature coax used for low power applications?
C, short lengths of coax mounted on printed circuit boards to minimize time delay between microwave circuits?
Or D, precision printed circuit conductors above a ground plane that provides constant impedance interconnects at microwave frequencies? Well, that's a mouthful. Microstrip. I don't exactly know what this is, so I'm going to have to do some heavy duty guessing here and ciphering. And I see stuff flipping by on the, nope, it's going to be all in the head.
Oh, okay.
Lightweight transmission line made of common zip cord. Zip cord transmission line? I don't think that's going to be it. Miniature coax used for low power applications. I've seen plenty of miniature coax, but I've never heard it called microstrip. So we're down to C or D. Short lengths of coax mounted on printed circuit boards to minimize. That doesn't even really make any sense to me. Short lengths of coax mounted on printed circuit boards to minimize time delay. D. Printed circuit connectors. That's got to be D, because I don't think it's A, B, or C. Precision printed circuit conductors. Precision printed circuit conductors above a ground plane that provide constant impedance interconnect. I don't even know what that looks like, but I think it's got to be D, because I'm pretty sure it's not A, B, or C.
Okay. I can see your logic. Can't talk, but I can see it. I can see your logic.
Just don't describe it.
Yeah. Everyone in the chat room saying D, except one answered not B. So,
Not B. Yeah, I agree it's not B.
Yeah.
If everybody else says it's D, I must be pretty close.
Yeah, Arnie says he's glad he's already passed the extra exam.
Me too, Arnie.
Yeah, we all are.
I don't study for these just to make them more interesting.
Yeah.
So it's really quite a challenge. Some of it I remember, some of it I don't.
Well, I'm going to agree with you. It is D. And you said you've never seen it, but that seems like the right answer.
Yeah, well, I don't think it's A, B, or C.
Yeah.
So I'm not sure what it looks like. I'd like to see what a microstrip looks like. So
Well,
unless the professor has some...
You are in luck.
my lucky day?
Yeah, it is. There's your micro strip right
Then actually,
there.
I have seen such as that before.
Yeah.
Then.
I thought you probably had.
Didn't even know it.
Yep.
Why are short connections used at microwave frequencies? A, To increase neutralizing resistance.
B, to reduce phase shift along the connection.
C, to increase compensating capacitance.
Or D, to reduce noise figure. Why are short connections used at microwave frequencies? A, to increase neutralizing resistance. I mean, I know what neutralization is, but I don't know what neutralizing resistance is. It's not A. Let's see. D, to reduce noise figures. No, it wouldn't do that. C, to increase compensating capacitance. You would use short connections? No. It's B, to reduce the phase shift along the connection, because microwave frequencies, your wavelengths are getting, pretty small.
Mm-hmm.
And so, a length of a conductor will have a time delay or a phase shift on a circuit. And if your wavelength's only this long, your circuit is going to have phase shifts in it at a much shorter distance than say, like HF, something like that. It's B, to reduce phase shifts along the connection. And everybody got that right. What would you have thought was the answer on that one?
I probably would have picked that one because I don't basically against the process of elimination again, just like the previous.
What is the power factor of an RL circuit having a 30-degree phase angle between the voltage and the current? Is it A, 1.73?
B, 0.5?
C, 0.8666?
Or D, 0.577? What is the power factor of an RL circuit? I don't know. You got the formula around here somewhere, Mr. Professor?
Yeah, but you can't just look at it and guess an answer. You could. Maybe some explaining is in order.
Yeah, that would be good.
All right. Well, let's do that then.
Okay.
When you think of it, the power factor, think of a mug of beer.
After I get finished with this, I may think about that.
Okay. So what we've got is the whole mug there, the liquid plus the head on the brew there. You can think of that as apparent power. And the way that's normally rated would be VA. If you buy a UPS power supply, it's not going to say how many watts it is. It's going to say how many volt amps it is. And if you do see the wattage listed on there, it's going to be in smaller print and it's going to be a smaller number, because some of your power will be wasted due to the reactive nature of your load. The active or real or true power would be the beer itself down there in the mug.
Okay.
Then the reactive power is the foam head on there on the top of it. All of that together is the apparent power of the circuit. However, the only part that's going to do any work is the active or real or true power of the circuit. So you got some wasted there. We look over to the left at the formulas there. We've got several. Apparent power in watts equals the voltage times the current. And like I said, if you buy a UPS, you're going to see the apparent power listed there, but they're going to probably call it volt amps. The real power will be the apparent power, which is the volt amps, times the power factor. And if you extrapolate that formula out or transpose it, the power factor equals the real power in watts divided by the apparent power, which is also in watts, but it's often referred to as volt amps. If you know the phase angle difference between the voltage and the current, you can just take the cosine of the phase angle, and that will give you the power factor. And I saw you had your pen out there doing some scratching, so that's going to tell me you have the cosine table in your head, and you calculated this out.
No, that's not telling you anything.
That's not what happened there.
That is not what it's telling you.
Okay. Do you want your battery-powered slide rule? Do you think that might help in this case? Or not?
I don't know if it's going to help or not. I guess we'll figure it out.
Okay. What is the power factor in an RL circuit having a 30 degrees phase angle between the voltage and current? So the only number you got to work with is 30 degrees. Back up and look at the beer again. Well, don't really
I
look
want
at
to
the
look at
beer.
it a little closer. I don't even drink, but I'm willing to learn.
Yeah, so I can teach you. Look at that bottom formula over there. Power factor equals the cosine of the phase angle. And we just happen to know the phase angle here. It's the only thing we know, and that's 30 degrees. Go to your scientific calculator. That's not going to be on your standard four-function calculator there. All right, so 30. All right, and now trigonometry on this one. And you see the cosine.
Okay.
All right. 0.866.
C. Well, I already said C before it came back.
Said C.
Okay. Man, I haven't looked at this
All right.
stuff like this since I was in high school.
Well, I haven't looked at it since I was in college. It's not something you need to know every day.
Yeah, I'm thankful for that.
And when I do need to know it, I just look in a book or look it up on the internet.
Uh-huh.
But you can't do either one of those on your exam.
No, you can't.
Yep.
So that's good to know.
Yeah. Let's see. What did they say over in the chat room there? I was not paying attention. Oh, yeah. We got a lot of C's in there. So some people knew the answer to it. Yeah, that whole volt amps thing is just, well, it's a thing. I don't like to see that when I'm looking at UPSs and trying to figure out how big a UPS I need.
Mm-hmm.
But, that's the way it's rated. That one right down there. I don't know if you can see it. There is a CyberPower UPS I just bought.
Still in the box.
Yep. It says it's 1,300 volt amps, and that's 810 watts.
Oh, yeah.
That doesn't sound like nearly as much, does it?
Nope.
Power is voltage times current until you got a power factor, and then it gets more complicated. But that's AC for you. All right, next question here.
What about that beer? Did we get that?
You can have that after the show. I'll have mine right now, though, in the opaque mug.
Yeah, well, this is about all I'm going to... In what direction is the magnetic field oriented about a conductor in relation to the direction of electron flow? A, in the same direction as the current.
B, in a direction opposite to the current.
C, in all directions, omnidirectional.
Or D, in a circle around the conductor. In what direction is a magnetic field oriented about a conductor in relation to the direction of electron flow? I'm going to go back to elementary school. I'm going to take a nail, and I'm going to wrap a bunch of wire around it and hook it to a battery.
Make an electromagnet?
Make an electromagnet. That nail is going to become magnetized. Well, it's going to act like a magnet whenever I put current through that coil. The magnetic field is not going to be oriented in the direction of the electron flow. It's going to be magnetized at either end of that nail, not just one end. Now, one end will be north and one will be south, but, the magnetic fields, so it's not going in the direction of the wire. B, in the direction opposite of the current. Now, because we could reverse the polarity, and we're still going to be magnetic at either end on the nail there. D, well, let's look at C. In all directions, omnidirectional. Yeah, my example really didn't prove that out, but D in a circle around the conductor, that's going to be the answer right there.
Mm-hmm.
Makes sense.
It does make sense to me.
And yeah, that's what they're saying. And Mike mentions the left-hand palm rule. There's such a thing as a left-hand rule.
Yeah.
Mike didn't just make it up.
If you're down below the equator in Australia, is it the right-hand rule for there?
We'd have to call up Peter and ask him. But no, I think it's still the left-hand rule.
So this makes me think of like if you're checking your current flow with an amp clamp, like an amp probe type clamp, that
Yes.
magnetism is all the way around the wire. And if you get that right in the middle, you get the most accurate reading if the wire is right in the middle of the clamp.
And that's because the magnetic flow is coming out around the wire. Yeah, good example. And it is D in a circle around the conductor. How many watts are consumed in a circuit having a power factor of 0.71 if the apparent power is 500 volt amps? Is it A, 704 watts?
B, 355 watts?
C, 252 watts?
Or D, 1.42 milliwatts? How many watts consumed in a circuit?
You want me to give you just a slight clue?
Yeah.
That may not help you. This is not the answer, but it's something you can think about. If the power factor was 1, then it would be 500 watts. Because it would be the same, but the power factor is telling you there's a loss. Since, the power 500. Factor is 0.71. Yeah, it's 500 volt amps.
Well, that's 355 volt amps.
No, all the answers are watts.
Yeah, I know, but the power was in volt amps, and I multiplied 500 volt amps times 0.71.
Okay.
I need volt amps. I need watts from the volt amps. Okay, I see.
Yeah, there's a little mix in the chat room there on it. Yeah.
Well, it's kind of a little bit tricky because the question has volt amps and the answers have watts. So, but I remember the glass of beer.
Yeah.
Thing.
But wattage is voltage times current.
Mm-hmm.
So volt amps and watts are really sort of the same thing. It would be if we were talking about DC, that'd be the same, But since we're talking about AC, then we got, the reactive components in there. So we got power factor involved in it. And so we're only 71% efficient. So that's why a circuit's using 355 watts out of the 500 you threw at it.
Arnie says 145 of beer foam.
I think he's right on the
he's
nose.
Right. Yeah.
That's it.
Arnie knows his beer foam, man.
See, I would have never gone exactly there, but if we went back and looked at that glass, and we got out our ruler and measured it, that's exactly what we would find.
That's pretty good.
Yeah.
That's good, Arnie.
All right, we're going to take a quick break. Now is the time to spice up your ham shack with ICOM's new, now shipping, ID52A handheld. This radio is perfect for staying in or venturing out and working your favorite bands this holiday season. ICOM's newest handheld amateur radio is a VHF-UHF dual bander with D-Star and FM dual mode functions. The ID52A is now shipping. This radio supports conventional FM communications and D-Star simplex, repeater, regional, and worldwide calls over the D-Star Internet Gateway. The ID52A is the first handheld amateur radio with a full-color 2.3-inch waterfall display and the ability to send photos over D-Star with a connected Android device. Other features include wideband receiver with guaranteed range of 144 to 148 and 440 to 450 MHz, simultaneous receive for VHF, VHF, UHF, UHF, VHF, UHF with dual DV mode. Integrated GPS GLONASS receiver, including grid square location, micro SD card slot, micro USB for data transfer, programming, and charge, and it meets IPX7 waterproof specifications. For more information on this and all the great ICOM radios, visit icomamerica.com/amateur. Calling all hams. Don't forget to find ICOM's booth at the 2022 Orlando Hamcation, February 11th through 13th. Well, what do you say we give away something?
Okay.
It's in the drawer over there. I didn't get it out. Yeah.
Not sure if I can get to it.
And yes, do be careful, Ed. You'll shoot your eye out. Oh, a shirt.
Yeah, I didn't even have to take the one off my back this time. How about
Oh,
we give away a nice ICOM Ham Crew t-shirt?
yeah.
Look just as good when you're leaving the Hamfest with all your goodies as you did when you got there with your pocket full of money.
Yeah. Good
They're
point.
nice shirts.
Yeah, they are. And whatever else Jesse can stuff in the box, because he usually puts something else in there as well.
Yep.
So,
So who won?
well, how would you win?
Well, if I were eligible to enter and I wanted to have a chance, I'd probably send an email to hamcollege@AmateurLogic.TV. You know, you don't even really have to have a call sign or anything to win this one. All you need is a name and an email address.
Yeah,
So
that is true.
And you know another cool thing?
Mhm.
If I didn't win this month, there's no reason why I can't send it again for next month.
Well,
Have another chance.
That's true, and you should, because we throw them away after every drawing.
Oh, you don't sell my email address? or
No, we
anything to
don't
anybody?
sell your email address. We don't harvest it. We won't spam you. Any of those.
Man,
things.
that's what I like to hear.
Yeah. However, if you do win, we will tell ICOM to contact you to get the size for your shirt and your address.
Well, that sounds fair enough.
Yeah.
Sign me up.
Okay.
Wait, I got to sign myself up,
Well,
don't I?
You're not eligible, but you are. So sign up today, and right before the show, I drew a random number and got a winner right here.
Awesome.
I don't know if he's in the chat room tonight or not, but it's well, let's just see what the email says. Hi, glad you are feeling better. KC9TPR. Bill or William Dabbs.
Oh, I'm pretty sure he's in there. I think I saw him a little while ago.
I think he may be in there.
Awesome.
And
Congrats, Bill.
yes, I am feeling better, and I think Tommy's feeling better too.
I feel better, just don't sound
Yeah.
better.
When you wrote this, you probably didn't know that Tommy had.
Yeah, I don't think I really
had it
said
too.
much.
Congratulations. ICOM will be in touch with you soon, and you'll be the best dressed ham at the next Hamfest. Speaking of Hamfest, I was just out of Hamfest this past weekend. They had the annual, I say annual, I don't think we had it last year.
The usually annual.
Yeah, the usually annual Capital City Hamfest here in Jackson, Mississippi, at the new Trademark this year. And yeah, they were back as a pretty good crowd there. A lot bigger area than we had before. I believe it's
Oh, yeah?
pretty good size. Pretty good selection of stuff on the tables, and we had some dealers there as well. Probably not as many as we've had in the past
Mm-hmm.
before the pandemic, but it's coming back. And it was really good to see a lot of friends down there that I hadn't seen, and I don't know, a couple of years probably.
Yeah, I kind of hate I missed it.
Yeah.
It was a little bit too early for me to get out around people, but I'm glad you got to go.
Yeah, I did, and I had a good time for you.
Well, I appreciate that.
Yeah, I didn't. The only thing I bought is a 1,000-watt dummy load that my friend Stan had down there. It's an old, I think that's a military surplus dummy load. It's pretty doggone heavy.
Yeah, I see that thing is huge.
Yeah, there's a little handle on it. I didn't know I was going to make it all the way to the truck. I had to stop and rest 3 times because it was pretty heavy. But anyway, I needed one at work, so I picked up that for a good deal.
How many watts are consumed in a circuit having a power factor of 0.6 if the input is 200 volts AC at 5 amperes?
Okay.
A, 200 watts.
B, 1,000 watts.
C, 1,600 watts.
Or D, 600 watts. How many watts are consumed in a circuit having a power factor of 0.6 if the input is 200 volts AC at 5 amps? I see you calculating over there. The known things are we've got 200 volts AC and we've got 5 ampere. So if I multiply 200 times 5, that's going to give me the apparent power, which would be 1,000 watts. If we multiply that times 0.6 for the power factor, 600 watts. And the way that you could have just looked at this and known the answer pretty much right away is, well, 200 volts times 5 amps. Well, that's 1,000. We can just look and tell that. And if our power factor is 0.6, well, we're only 60% efficient. So the only answer close would be 600 watts, because there's no way it's going to be 1,000 watts. There's no way it's going to be 1,600 watts. 200, yeah, that's an awful lot of loss. D, 600 watts.
Perfect.
All right, and if I look back in the chat room, I think, yeah, everybody pretty much was on top of that one right there with a D. What happens to reactive power in an AC circuit that has both ideal inductors and ideal capacitors? A, it is dissipated as heat in the circuit. Let me just say, I'll just mention what ideal inductors and capacitors are. We'll just say they're inductors that have no resistance to them.
Okay.
Or capacitors that have no resistance, and they're ideally exactly what they're specified to be. There's not any impurities in it. So, A, it is dissipated as heat in the circuit.
B, it's repeatedly exchanged between the associated magnetic and electric fields, but is not dissipated.
C, it is dissipated as kinetic energy in the circuit.
Or D, it is dissipated in the formation of inductive and capacitive fields. Oh boy. Okay. What happens to reactive power? An AC circuit has both ideal conductors and ideal capacitors, dissipated as heat. But if there's no resistance, I'm going to say that's probably not it. B is repeatedly exchanged between associated magnetic and electric fields, but it's not dissipated. That seems plausible. C is dissipated kinetic energy, or D is dissipated in formation. I'm going to go with B. I'm not sure if it's right or not, but I think it's probably as good a chance as any, since you say that ideal means there's no resistance. So I'm going to say it's repeatedly exchanged between the associated magnetic and electric fields, but it's not dissipated because there's no resistance.
Sounds like a
good guess.
Good
That's
guess.
a wag?
Yeah, I would say, yeah.
You know
wag?
what? Wild.
No. Oh, yeah. Okay. Yeah. There's some mixture on that one in the chat room. I thought there might be. But I'm going to agree with you. I'm going to say it's B.
I got it right.
I think you
Awesome.
do.
How can true power be determined in an AC circuit where the voltage and current are out of phase? Oh, I'm glad you got this one. A, by multiplying the apparent power by the power factor.
B, by multiplying the reactive power by the power factor.
C, by dividing the apparent power by the power factor.
Or D, by multiplying the reactive power by the power factor.
Out of phase.
How can the true power be determined in an AC circuit where the voltage and current are out of phase? Well, there's always going to be some phase shift between them in an AC circuit. A, by multiplying the apparent power by the power factor.
That's why I'm going with A.
Yeah. I think I'm going to go with that, and we may have found that first wrong answer for tonight. Let's see what... There's not a lot of help over in the chat room on this one.
Well, they're still looking for the beer.
Yeah.
Arnie's looking for the beer. We may need that beer.
Yeah. Well, let's see. We were doing that earlier in the show tonight. Some of the first questions, we were taking the apparent power and multiplying it by the power factor. And that gave us the true power or the real power. What is the power factor of an RL circuit having a 60 degrees phase angle between the voltage and current? Is it A, 1.414?
B, 0.866?
C, 0.5?
Or D, 1.73? Is this not the same thing we had earlier? That was 30 degrees, wasn't it?
Yep. I'll give one hint here. Two of those, there's two answers on there that you know immediately those can't be it. A and D, both of those numbers are greater than 1. Your power factor
that's true.
is never going to be 1 or above. If it's 1, it's 100% efficient. There is no power factor. And it can never be more. That means you're actually gaining energy by having a power factor, which we know that's not right.
That was 60, right? 60.
60 degrees.
And we're going to do the cosine of 60, which is 0.5.
That is
C.
C.
How many watts are consumed in a circuit having a power factor of 0.2 if the input is 100 volts AC at 4 amperes? A, 400 watts.
B, 80 watts.
C, 2,000 watts.
Or D, 50 watts. All right, I'm just going to do this old school here. So the first thing I'm going to do is figure out my apparent power. So I'm going to say 100 volts times 4 amps. That would be 400 watts of apparent power.
Mm-hmm.
And then the power factor is 0.2. That means this is a really lossy circuit here. So 400 watts times 0.2. Well, I know it's not 400 watts. It's not A. And it's not C. I mean, it's not 2,000 watts. It didn't actually increase. It's either going to be 80 or 50. And so 400 times 0.2, I'm going to say it is 80 watts.
I concur. Because I already did the math over here.
Yeah, chat room's all saying 80, so I was a little slow, but I got there. All right.
That's all foam, no beer.
That's true, man. That's not even...
Somebody's getting ripped off big time.
Yeah, big time. You might want to look at improving your circuit a little bit if it's...
you get a better bartender.
Yeah. How many watts are consumed in a circuit consisting of a 100 ohm resistor in series, the 100 ohm inductive reactance drawing 1 amp? A, 70.7 watts.
B, 100 watts.
C, 141.4 watts.
Or D, 200 watts. How many watts are consumed in a circuit of 100 ohm resistor in series with 100 ohm reactance drawing 1 amp? It's going to be B, 100 watts.
Okay. How'd you come up with that?
Well, it seems to be the obvious one. 100 ohm resistor, 1 ohm inductive reactance. So I don't understand the inductive reactance too much, but it's got to be 100. There's too many hundreds there. How do you calculate that?
How do you calculate that? Well, funny you should ask.
Yeah,
Because
but I do think it's 100.
I just so happen to have two transparent,
What's this?
pretty much. Yeah, they're green. But I've got the ARRL's extra question and answer book, and I've got Gordo's extra class license study guide. And I looked this one up in both of these a few days ago just to see how they went about figuring them out. Completely different.
Really?
Yeah. The ARRL one had a big formula, a lot of calculations in there, and they were taking into account the 100 ohm resistor and the 100 ohms of inductive reactance. And pretty good size formula in there on it. Gordo's, he said, first thing he said, if there's no capacitance in that circuit, it's only an inductive reactance, you don't have to worry about that 100 ohms of inductive reactance. It's not going to consume anything. So then we're down to just strictly using one of the
100
power
ohms in
formulas.
1 amp. That's for 100 watts.
Well, P equal I squared times R is the formula. All right. What is I squared? I is current.
Okay.
So I squared is 1 times 1, which is 1. And then times R. The only R we're worried about is the resistor. So you're right, it's 100 ohms.
It's 100.
Yeah. If it had been anything other than 1 amp, it would have gotten a lot more complicated. But since it was 1 amp there, I squared, is
Interesting.
it's still 1.
Unless they're in series.
Verify that. Yep. So I thought that was very interesting.
It is interesting.
Yeah, that the ARRL had a lot of math in there that accounted for the inductive reactance, and Alan Gordo just said, forget about the inductive reactance. It's not going to have an effect here.
Doesn't matter.
Yeah, P equal I squared times R. Pretty common power formula.
What is reactive power? A, wattless, non-productive power.
B, power consumed in wire resistance and an inductor.
C, power loss because of capacitor leakage.
Or D, power consumed in circuit Q. What is reactive power? Wattless non-productive power. Possibly. B, power consumed in wire resistance and an inductor. No, reactive wouldn't be the resistance of the wire. That's resistance of the wire is resistance. C, power loss because of capacitor leakage. Nah. D, power consumed in circuit Q. No, it's a wattless, non-productive power.
Yeah, it's got to be A, the beer foam.
Yep, the head on the on the beer. So there you go. It's a little mixed in the chat room, but mostly A's.
You know, if I do a project where I have to deal with this, I might have to go buy a 6-pack just to kind of figure.
One final question for you tonight. What is the power factor of an RL circuit having a 45-degree phase angle between the voltage and the current? Is it A, 0.866,
B, 1.0,
C, 0.5,
or D, 0.707? 45 degrees? Going back to the calculator. I'm sorry.
Nearby calculator. Okay.
It was 45?
Yeah, 45 degrees. Cosine.
D, 0.707.
Okay. I see how you could say that.
Guess that's the answer.
Yep. And everyone in the chat room saying that. So there you go. D, 0.707. And that, my friends, yeah,
it's
that's all.
interesting. The terminology is just interesting. The phase angle, I don't know. The terminology is interesting to me.
Yeah, well, the phase angle is a real thing. I've said it before. When I was studying electronics in school, just breezing through in DC circuits, no problems. I just kicked back and, made hundreds. And then we got to AC and life got complicated all of a sudden.
I can understand.
Very complicated. Because when you start shoving AC through a circuit, the voltage and current don't come out at the same time. And that phase angle can account for huge differences. I guess that's going to do it for tonight. Thanks everyone for joining us here on Ham College. Some interesting questions. I'm going to say not the hardest that we've had, and certainly there's going to be a lot more harder ones coming up yet. Study if you're looking to take your extra or any amateur radio exam. 2 choices of study material here. Gordon West Extra Class Study Guide for 2020 through 2024. So it'll be 2 more years before they change the exam pool again. So now would be an ideal time to study because, you'll get your studying done before a new pool comes out. Otherwise, if you're half studied up on the old material and the new exam comes out before you finish, you'll
have
probably
some
have
catching
some
up
more.
to do.
Yeah. Or the ARRL's extra Q&A book. That just looks weird, doesn't it?
The transparent book? That's so cool. I'd buy one of those books just for the transparency alone.
Yeah, but, it doesn't work like this. Well, some stuff it does. And one other, and I've mentioned it before, I kind of like this one. ARRL's got the extra question and answer book, but they've also got this one right here, the Extra Class License Manual. This is a thick, spiral-bound book. If you just want the questions and answers, this one gives you just the questions and answers, maybe a little paragraph or 2 on how to get the answer. Gordo cuts right to the chase, gives you the question, the answer, and any shortcuts that he could come up with or memorization tools or ways to remember how to figure things out. Excellent study guide there, one of my favorites. But this one goes into detail. This one gives you an in-depth study, so it's, most of the book is not even questions and answers. It's got all the questions and answers in there, but it's also got a lot of theory and background. So, if I was studying for my exam, I'd probably take, one of the thinner books. But really, if you wanted to know what was going on in depth, that's pretty hard to beat.
That's probably a good reference book to have even after the fact.
Oh yeah, definitely. I look in that on some of these when I'm putting in the questions and trying to figure how I'm going to explain that. I look at all three of these.
Mm-hmm.
Also, there's online study guides where you can take practice exams. Hamstudy.org is one, that we've recommended. There's several others out there too. So do your study, go take your test, upgrade your license. If you're not a ham yet, go back to some of the early episodes at Ham College, learn about the technician exam, and get started. Technicians, look at the general there. You might want to upgrade and get on HF. So with that, any final thoughts tonight, Dean, before we go?
No, appreciate everybody joining us, and it's been fun. It is. I saw his comment on there. It's good refresher material. If you have already got your extra, it is great refresher material.
Oh yeah.
So, but anyway, appreciate y'all joining us, and we'll see you in a couple of weeks for AmateurLogic.
Yeah, it'll be on Friday, February 18th. Yep. And just be warned, we have a viewer from out of the country who has sent us a package. We don't know what's in it yet. Email received one as well down in the country of Louisiana, and Mike up in Canada.
The country of Canada?
The country of Canada, yep. So we don't know whether to expect a wild haggis in the package or exactly what's going to be in there. So join us on the 18th, and we'll do the reveal and cut the tape and see what's in those.
Cool. That should be fun.
7-3.
7-3, everybody. What?
Gave me a weird look and said, what? If there's no capacitance in that circuit, it's only an inductive reactance, you don't have to worry about that 100 ohms of reductive